And the speaker that is kicking off this afternoon session is Don Coolen, who will tell us about a replica analysis of overfitting in generalized linear regression models. So please, Don, try to share your screen.
Sharing. Okay, can you see it now?
Yeah, we see your slides, not full screen. Yeah, full screen now. Okay,
screen.
and we hear you.
Okay.
Go on.
So thank you, Lenka. So let me start with this talk. We all know what overfitting is. Overfitting happens when we have a model that is too complicated relative to the number of samples in the data. And if we have such a learning scenario, then the model starts to mistake noise for signal. And you get predictions and regression outcomes that are very unreliable. And so that's what this talk is about, trying to understand and more specifically trying to model the relation between the parameters that comes out of your inference method and the true parameters in the regime where we know that overfitting happens. And the motivation behind that is that if we can compute or predict analytically the relationship between what your regression method reports to you and what the true parameters were, then we could correct for the errors that are made as a result of overfitting. And since I've been working quite a lot on medical data, that is an area where it is particularly important, because in post-genome medicine, we can measure many, many things, but the number of samples we have, the number of patients in clinical trials, for instance, is still very small. So I'll start with the introduction. And because the motivation for this came from medicine, I start initially with an area of regression models that is called survival analysis. And then I will gradually work my way to the more generalized setup, where we find that the method that was initially developed for survival analysis can in fact be generalized to arbitrary generalized linear models. So this is the structure of the talk. Let me start with the introduction. So let me introduce quickly to you what survival analysis is. Survival analysis is simply the situation where you have data that each sample comes in the form of a pair of a vector Z that gives to you values of things that you can measure at time 0 in a patient, for instance, and then a corresponding time that tells you at what time later this patient died or got a relapse or got whatever you're technically interested in this particular study. The crucial thing is that these are event times that have the property that once a person is dead or had a relapse, I can no longer guess what would have happened afterwards. So these are particular type of data. And so this is what you have. You have time 0 when you make all kinds of measurements in your patients. These are the vector Z. Then you monitor your patients and you record the time along the time axis here when they died. Then you collect all these data. You have a data set with pairs of these vectors, which are called covariates, and the event times. And what you try to do is you try to find out whether there are patterns that somehow give you some structure that allows you to predict, possibly partially, the event times from the covariates that were measured at time 0. And it's clear why in medicine this would be very desirable. It would allow you to identify early on which are the high-risk patients. It would allow you also to maybe discover disease mechanisms if you find that certain components of this vector play an important role in increasing risk. And it also allows you sometimes to design new treatments, because some of these variables that could be things that we can actually change. So this is the context, but this methodology is not just used in medicine, also in economics, in the study of industrial processes and so on, where failures happen. And in medicine, the dominant model that has been around since the 1970s, and that still is used in at least 95% of all medical papers, is a regression model for this type of data that is due to David Cox. And the idea is as follows. It's not a very complicated model, but first of all, one can always write the probability distribution for the event times, given the covariate set, in the form of so-called hazard rates. And these hazard rates that are written as H give you the probability per unit time that the event will happen now, but conditional on the fact that the event hasn't happened yet. And this is where this irreversibility comes in. You cannot die more than once. And that gives you the extra factor here that accounts for the fact that you have to be alive to die now. So this is general. This is not a model. You can always write things in this way. What Cox did, he made a specific proposal for this hazard rate in which he separated the time from the dependence on the covariates, which was written in this particular form. Now, the reason why this turned out to be very, very useful is that if you work out the mathematics of, for instance, maximum likelihood inference, where you find your parameters, which in this case are the vector beta and this function of time lambda, you find these parameters by maximizing the data likelihood. That's maximum likelihood regression. And this would then be the recipe. You take the logarithm of the likelihood. That looks a bit nicer. But the crucial thing is that for this particular choice, you can maximize over this function lambda first and compute lambda analytically. That's the crucial property. So you can express the solution of the maximization for lambda in terms of the remaining parameters and the data. So that beta still sits here and the rest are all data. This then you plug back into the function you're maximizing, and only then you maximize over beta. And that means that the most awkward object here, which is a high dimensional, infinite dimensional object, has in fact become harmless because you can compute it analytically and you only have to worry about finding these parameters. And this, of course, especially in the time when he did his work, was vital in order to do anything, that we could do it on the machines of the 1970s. And this is the basic model. There are, of course, many extensions, versions, things become more complicated, but in essence, this is what it's about. And of course, like every model, also this model is subject to overfitting as soon as the number of variables, p, that you measure becomes of the order of magnitude as the number of samples. And you can easily do simulation experiments where you start with all your covariates, so with large p, and you do a separation into training and validation set. You train the model and you check its performance on unseen data. And then you iteratively reduce the least informative parameter and you do it again. You get these typical curves that show you performance of prediction versus the number of variables that were used. And this is the fingerprint of overfitting. Everyone who's worked in machine learning recognizes these curves. And what was missing in medicine so far was a recipe for instance, telling you where is this optimal point, where the training performance and validation performance are still similar, and can we actually find out which is the set that gives you this optimal point, which is the selection of variables. So this was the starting point of our work in this area. We tried to see whether some analytical work could be done. And then if we did simulations, we found something that was rather interesting and useful. And what we did is something very primitive. If you just look at this as an example, this diagram, we plotted in synthetic data, we plotted the true value of each of these coefficients, beta, versus the value that comes out of the regression method. And in an ideal regression protocol, you would find, of course, the true value to be identical to the inferred one, and all the points should be on a line. Now, this should happen when the ratio of number of parameters over samples is small. But if you increase that ratio, you know things will go wrong. But you see here that they go wrong in a very special way. There is not just a data cloud that widens, but it starts rotating. And this rotation tells you that there is a predictable bias. If I knew this angle beforehand, I could just map these points back to the diagonal, and I would be able to account and deal with most of the errors made as a result of overfitting. And in fact, the same happens. You get very reproducible biases also in this function of time. Remember, this was the model. So there's this other parameter, this function of time. And that's a bit easier, if you plot the integrated version of this object, then the dashed line is what you should have found in an ideal scenario without overfitting, but you get increasingly an overestimation of this function here and an underestimation here. And this is not dependent on what choice you make for this function lambda. You get the same phenomenology here. So again, in all the parameters, it seems to be that yes, there is noise as a result of overfitting, but the dominant effect is not noise, but a bias. And that means that we are in business. We could perhaps predict that bias. So now we need a bit of intuition for the problem before we know how to model this. And for that, we just go back and ask ourselves what maximum likelihood really does. Now, maximum likelihood is this idea that you determine your parameters on the basis of the criterion that you want the likelihood of the data given the parameters to be maximized. Now, that can be rewritten in a way that has been noted earlier, of course. as equivalent mathematically to the minimization of a Kullback-Leibler distance. And it is the Kullback-Leibler distance between the parameterized model and the empirical distribution of the data. So the empirical one is just, if you wish, the histogram of the data as you find them. And this Kullback-Leibler distance between the model with parameters theta and the empirical distribution is what maximum likelihood de facto minimizes. So intuitively, this is what it does. It tries to move the parameterized model as close as possible to the empirical distribution. And you can see that that makes sense in a certain context. If the dimensionality of the thetas is fixed and n goes to infinity, then we know that the empirical distribution will converge to, let's say, let's assume that the model was chosen well. It will converge to the model distribution with the correct parameters, provided we keep p fixed and we send n to infinity. And therefore, if you minimize the distance between p hat and a parameterized distribution, you will get your correct parameters out. But this is no longer the case in the overfitting regime, because there is no sense in which the empirical distribution converges to the distribution of the model with the correct parameters. This is a very sparse thing. And this is the reason why overfitting is occurring. You are trying to fit a model to a very sparse representation that doesn't look like the distribution from which the data were drawn. Okay, and if we also look at MAP regression, the other protocol where you include, in addition to the data likelihood, a prior, then you just get minor changes, but you have to be aware of certain scaling aspects. So in MAP regression, we add a prior. So what you're now minimizing, maximizing is this. These are just the definition again of the model. And you would include priors like the L1 prior or the L2 prior. And they will come with a parameter that gives you the width of the distribution, basically. Now, the claim that I would like to make is that this width, in fact, should also depend on P in the overfitting regime. And there are two arguments. First of all, it comes out with the general theory later, but there's also a very simple scaling argument. Namely, that if you assume that these betas are order 1 objects, then a sum like this, which occurs in all these generalized linear models, also here, would typically start scaling as square root p. So for large p, a sum like this would diverge to plus or minus infinity, and that means in the context of the present models that all your observed event times would either be 0 or infinity. The very fact that we know that we have finite event times in our data set means that these dot products have to be order 1, and that means in turn that the betas have to effectively scale as 1 over square root n. So one cannot assume that these hyperparameters are independent of P, not in the overfitting regime. Okay, so let's now see how that theory of overfitting is built, what the basic ideas are. So we go back to the interpretation of maximum likelihood regression as the protocol that minimizes the Kullback-Leibler distance between the empirical distribution, where data were drawn from a model with parameters theta star that we don't know, and the model with parameters theta. So if you ask yourself, what would be an optimal outcome? It would be where your model stops when theta is equal to theta star. So not at distance 0, but where the distance between the empirical distribution and my current model is the same distance as between the empirical distribution and the true model. And this distance is no longer 0 when we are in the overfitting regime. So what you can then do is you can construct this quantity, the minimum that is achieved by the regression protocol minus the value that you should have found in an ideal scenario. And that means that if you look at this quantity, it tells you whether you're overfitting or underfitting or doing a good job, in the sense that if this is larger than 0, this means that you should minimize further, you're underfitting. If it's less than 0, you've minimized too far and you're overfitting. So the relevant information seems to come from the computation of this quantity. We're not interested in those things that are dependent on the realization of the data set, so we average this over all possible data sets, and then we plug everything in. We have the definition, we put all these Kullback-Leibler distances in, you get some terms canceling, and at the end of the day, you get this quantity. It's the average over the data set of the minimum of some sort of cross-entropy term. Okay, so this is what we would like to compute analytically. And the first problem you run into is that you have this minimization here. It's very hard to minimize analytically and then do the average all in one go. But of course, this is where statistical mechanics helps us. Minimization can also be done by using concepts like free energies, Laplace identities. So we can trace the minimization for a differentiation and an integral. Yeah? So we can say this minimum can also be seen as the ground state of a statistical mechanical problem. And we just compute a free energy and calculate the ground state. So instead of having a minimum, we will now have an integral and a differentiation to do. And looking at ground state then means that there's this parameter gamma, which is like an inverse temperature that has to go to infinity. Using this means that instead of having this formula here, we lose the minimization, the price we pay if we have an integral over all parameters now. So it's like a stochastic minimization with noise of the strength 1 over gamma. The final problem is we have an average of a logarithm, and that's where, again, we have a nice trick from physics. We have the replica method that allows us to use this identity average of a log expressed in terms of a limit of the logarithm of powers of the argument. Applying that here means that instead of having the log and then doing an average, we can get the log of an average. But inside will now be the nth power of the original object. But this original object was an integral, so we can write that as a repeated integral. And then it turns out we can do the average over the data set, and what rolls out is a very nice, completely explicit quantity that we can start to compute. That was the idea. Now, if you do MAP, there's only a very small change. So MAP means adding a prior. I've just shown you in red what the changes are. You minimize something slightly different, and the only thing that changes is you get priors popping up inside that integral, nothing else. Another nice aspect is also that if you want to do the base optimal estimator rather than MAP or maximum likelihood, that follows in fact from not taking gamma to infinity, but choosing gamma to be equal to 1 in this quantity, which is like a free energy. Okay, now translating that to the Cox model means making a choice now, and this was the Cox model. It has this awkward expression with exponentials inside exponentials. Psi is just a shorthand for this renormalized dot product, and the square root p came from the argument that we gave earlier. So now our betas can be seen as order 1 quantities. Big lambda is just the integral over the small lambda. So in this model, our parameters are a vector and a function. There's another nice aspect of the Cox model, is that you can show that the average and the covariance of the covariates can be transformed away. So you might as well choose this to be 0 and have uncorrelated z's. And that leaves us just with one crucial assumption we need to make. We assume that the covariate distribution is such that these dot products seen as quantities where the z's are the random variables, so the betas are now fixed still, that these are Gaussian, which comes from the central limit theorem. If the z's are only weakly correlated, which they are here, or you could choose the z's to be Gaussian and you have it directly for any b. Then, I won't give you details, but then you run the standard machinery of statistical mechanics. You do your manipulations, you have integrations, and because some of these parameters are functions, these will become part integrals. You do steepest descent, you take your limits, you make the replica symmetric ansatz, and you get a theory phrased in terms of these quantities here. And if you look at them, they give you things like the angle between the inferred parameter and the true parameters, things like the magnitude of the inferred parameter vector. But you can already feel intuitively from this type of information follow the details of these data clouds that I gave you earlier. If you want to see what the things look like, then you find an explicit formula. You find an explicit formula for this overfitting measure E, which turns out in the limit of large N and large P with fixed ratio only to depend on two things, namely the ratio of number of variables over number of samples and the rescaled magnitude of the true parameter vector. So the details of that vector drop out. They're not relevant anymore. And after a simple transformation, you get 4 closed equations. From these 4 equations, you solve your order parameters and you can compute anything you like. And 3 of them are scalar, but 1 is a very nasty functional equation, because the function lambda is to be solved here, but it sits also inside the integrated version, and then you have the Lambert W function, all kinds of nonlinearities. This is not an easy thing. But once we have these order parameters, we can compute the slope and we can compute the width of the data cloud. Then Finding this lambda is harder. You can do expansions for large time. You find the leading order. That suggests that in leading order, the relationship between the big lambda and the true big lambda would be like a power law. And you can use that as a variational approximation. And if you plot log-log, you see that this is in fact not just for large times, but also very well performing for small times. And then you can build your theory, you can do simulations and see whether the predicted width of the cloud and the slope of the cloud agree with the simulation data. And there will be deviations, and that's purely because of the variational approximation one has to make. If you include MAP inference, there's a couple of changes, but it doesn't change structurally. So now, knowing that, as I showed before, we need to choose our hyperparameter wisely in a way that depends on P. If you have an L2 prior, that means you have to have P here, and the eta would then be order 1. So we have a new hyperparameter. If you have MAP inference, you can no longer transform away the covariate correlations, and that means you get a theory that involves the spectrum of this matrix. You get 2 extra order parameters, but qualitatively, the theory remains very similar. You just have now 5 equations instead of the previous 4. So these are scalar equations, and we still have this functional order parameter equation. And if you compare the predictions in terms of the order parameters with simulations, you see that the agreement is really good, even if you have correlated covariates. Here it looks like there is deviation, but the error bars are also really large because you get large finite size effects. Okay, so this was done, and not so long ago, and pretty soon you realize that what is essential in this all calculation is not that this was a Cox model or that even the outcomes are time to event data, but this is a fairly generalizable approach. So we now look at arbitrary generalized linear models. That means that we have vectors that come in, you can see them as questions, we have answers that are variables that come out, S, and the only thing we assume is that the dependence of S on Z is via a dot product. So the Z's appear nowhere else. We can have an army of other parameters, and they could even be functions. That's not relevant. And you see there is a very large family of models where this structure is there. So what we've seen so far is the Cox version, where S is a time, so non-negative. We have, of course, linear regression, which is the simplest case. We have logistic regression, neural networks, but simple ones for now, so binary perceptrons. Ordinal class regression, where you predict one of a number of discrete classes. All these models just differ in what is this function P, but they all have this general form. Okay, and now it turns out that you can fairly easily generalize theory. And the result is this. I've indicated just with red where this function P actually sits. So in your order parameter equations, it appears here, here, and in the definitions of what some of these averages mean. So these are averages over distributions of the outcome variable where the model also appears. Here could be a sum if S is discrete. And there's this tricky function here in that psi that appears in various places that involves P. But the message is that you can forget about all the replica calculations. You can take this as a starting point if you're only interested in correcting models that are of the GLM form for overfitting. You don't need to know where it comes from. You can take it here, you substitute your favorite model, and you work out these equations. And there's more that came out. We could also prove that for arbitrary generalized linear models, we can actually calculate the following expressions for the expectation of the inferred model parameters and for the correlations in the inferred model parameters. And you see the expectation always depends linearly on the true parameters, but there could be mixing, and there generally will be mixing. So this is not a diagonal matrix. There will be mixing as soon as you have a regularizer, and the matrix A, the covariate correlations, is not a simple diagonal thing. So matrix correlations give you mixing of the inferred parameters. But having these relations allows you now to do the following. You can design decontamination protocols where you say, look, I know that beta hat comes out of my imperfect regression method. Can I construct a matrix F such that from this original regression outcome, I compute a new one that has all kinds of desirable properties? And then it depends on what criteria you use. You can say, I want the inference bias removed, immediately you get a very simple expression and you have all the information from your replica theory to calculate this thing. Or you could say I want a minimum squared error. I want the expected mean squared error between the inferred, which is this, and the true parameters to be minimized. Again, you can work it out analytically and you get an explicit expression of which all ingredients you have. One thing I also thought was sensible, turns out not to be, is to minimize the expected generalization error, because you can see in examples that this is not generally optimal. You can get all kinds of funny things happening here. But these two are sensible. In practice, you also need to estimate some quantities, but in view of time, I will not go into detail, but you need to estimate the true covariance matrix and the length of the true parameter vector, but you have additional identities for this. Now, as a test, simplest case, linear regression. In a nutshell, you find everything that you hope to find. You find the usual thing that there is no bias. Linear regression is the only case where there is no bias. You can also see the inferred noise parameter going to 0 close to the transition point, and that shows you that in linear regression you start mistaking noise for signal. And in fact, when you want to compare things, it is rather interesting because the exact solution for linear regression is formulated. You can work out the equation directly in terms of the empirical covariance matrix of the covariates. And this thing is not the true one from which the data were drawn. So we have a replica theory formulated in terms of A, and we have the direct solution formulated in terms of A hat. And they have different spectra, different statistics, but with a bit of work, you can show that you can compute for the linear case the distribution of inferred parameters, and from this you can actually derive that the replica theory gets it right, that you can go from the empirical to the true matrix, although they are certainly not the same. You can do various Wishart integrals and show that the theory is correct. Now, the second test is the Cox model, which rolls out of this more generalized setup. And the third model I want to show is a model for which this wasn't yet done, overfitting correction in logistic regression as an example. And you see here order parameters as predicted by the theory, dashed lines, and as measured in simulations versus the ratio of parameters over samples. And you see the agreement is really nice. And this was in the case of uncorrelated covariates. Now for correlated, well, there are so many things you can vary. So we have a parameter epsilon that measures the correlations across covariates. We have eta, which was the hyperparameter of the prior, and we have the magnitude parameter of the true parameter vector. But in a nutshell, the theory, everywhere where you test these things, the theory is describing perfectly the simulation. So lines here are theory, markers are simulations. And this is the test of these correction protocols. So let me explain that a bit for the previous cases. So you can plot the slope of this data cloud, the data cloud that I show here, for instance, yeah, the true versus inferred parameters that ideally should be on the diagonal. So in red, you see what comes out if you just do your maximum likelihood, or MAP in this case, inference. Blue is the slope that you find after applying this correction protocol that should remove the bias. And you see that indeed these slopes in all these cases are more or less equal to 1. Then green is the other protocol that says, no, I don't care about the bias. I want to minimize the mean squared error. And you see that if this is what you do, indeed it corrects and it has the lowest value of all these examples. And it depends on what your criterion is, which one of these you use. Then another problem that is known from a logistic regression is that the bias, the intercept parameter, is also subject to overfitting. And you see the theory predicts also that perfectly. Dashed line is prediction, markers is what you find in your simulations. Okay, so I hope I've done well with time. Let me summarize what I've shown you. So I was interested in overfitting initially in survival analysis, and we developed this analytical approach based on the replica method, where in maximum likelihood regression, you get closed equations, and the equation we got for this function was hard to solve, so we did a variational approximation. Then in MAP, it just gets a bit more complicated because you can no longer transform away the covariate correlation matrix, so the spectrum of this matrix comes in, and you get this p-dependent hyperparameter. Then the generalizations is what we've done most recently and what this talk was about. you could show that this method can be developed to apply to arbitrary generalized linear models. The only crucial ingredient is that the dependence on the covariates is channeled via a dot product and nowhere else. And we could find explicit decontamination formulae, and it depends on what your criterion is, what you want to decontaminate for, how you should decontaminate it. And we had applications to linear regression, logistic regression, and we also recovered all the previous survival analysis equations from this. So far, we've only done some examples. Of course, I could also do the ordinal class regressions. There are many generalized linear models. And other extensions that we are now looking at are those, for instance, where you have not one dot product, but multiple ones, which is the case in multi-layer neural networks, which is the case in survival analysis with competing risks, or where this dot product is no longer described by Gaussian statistics. Or another area is where you don't have input-output models, but you have parameter inference in exponential families. For instance, when you want to infer graphs, like in direct coupling analysis. And also there we can see that the same methodology can be used. So this is where I want to end. I would like to thank the people that have contributed to this work. So Fabian, Fabrizio, James, Alexander, Pierre, Conrad, and Mansour. Funding, some of the postdocs and PhD students had funding from some UK institutions. And if you're interested in reading, the first two papers are on survival analysis. One is maximum likelihood, the second is MAP. And the most recent generalization is now in press, but it is also on the archive. Okay, thank you very much for your attention.
Thank you, Ton. You did perfectly on time. So we have the 10 minutes for the discussion as planned. So I don't see any questions on the chat. So if there are some questions, there is maybe one, but otherwise just feel free to step in. There is Florian Margard that is asking a question. Do you want to ask it, Florian, in real, or should we just read it?
Okay, I can hear me. I'm just interested in the empirical status for deep networks. Have there been any experiments on overfitting that would not, as you nicely did, be inferred versus the true parameters, and that would then observe a similar systematic deviation from the diagonal? Is that something that has at least empirically been studied?
The first part I could not hear very well, but I thought you mentioned in multi-layer neural networks whether something similar happened. Is that
have there been experiments on overfitting in deep networks, plotting inferred versus true parameters, e.g. when generating the data using a network? Okay. Would you observe the same systematic deviations from the diagonal when overfitting?
So my answer would be that I haven't checked that yet, but I would be very surprised if it wasn't the case, because I've already started doing the theory, and you see that the theory looks pretty much the same. You just get some extra objects where you had matrices, you get tensors and all that. But probably, Lenka, you might have done that yourself, or with your colleagues in Paris, because you've looked at multi-layer systems, or Mark Mizar, no? Is that
something? So that depends. I guess it's kind of that question's related to a question that I had for you, because you, in your analysis, you assume that there is a beta star, and that the kind of the labels, the S, I believe you call them, do come from the same model, assuming that beta star, right? Which is a kind of a very strong assumption in the real world. I guess in your medical applications, you clearly must see this is not the case. And how does it then? How does that kind of invalidate or influences the theory?
Okay, so it is a very good question, and of course this is one of the things I could have added to the list of things to do, because it's certainly very important. Let me tell you what I think will happen, and I can bet you a few Mars bars that is what will happen. So in the theory, you get always the occurrence here of the object which represents the model that generated the data. It also always sits here. And that it represents the model that generated the data is because you don't get the order parameters here as the argument. This quantity is just a dot product, right? And this thing tells you that the dot product is proportional to the amplitude of the true vector. It is a Gaussian type thing, and there is no order parameter appearing in here. My guess is that if we had two models, one used for inference, call that P, and one that generated the data, call that Q, you would just see that Q sitting here and not the P. You would see it here, you would see it here.
Yes, but you would still need the one that generates the data to be of the type of the generalized linear model. You would need it to depend on the scalar product, and that's still a strong assumption for the real construct.
Yes, that is certainly true. So I think once, if one is happy to accept that, then it is very transparent how this would turn out to be, and you just get the actual model sitting in certain places rather than the assumed model. If it's no longer a generalized linear model, then the party is over, at least for now, and you have to think again. And I don't know what would happen in that case.
Yeah, so I guess the question that Florian was asking about the deep networks is kind of, you know, you would think of using deep networks if the labels come from a, you know, much more generic model than the generalized linear model, and so now I think you answered that question. Why would one would basically have to rethink what would become to this term when the labels come from this more generic model.
Yeah.
Cool. Yes. And that's kind of challenging. We tried, but didn't succeed so far.
I'm not surprised. No.
So there is another question by a host. I have a question. Who is the host currently?
That's me.
Ricard Hilbert. Okay, good.
I think it's me.
Go on.
Yeah, so I had a question about, so maybe it's just to clarify my understanding, because you're talking about bias in the estimation of the parameters.
Yeah.
But you're also adding a prior. Now, often these priors are also shrinking. The priors, so if you do the map estimate, the prior themselves introduces a bias. Yeah. So how this is your replica correction taking both into account, or is it?
Oh, yes. So it's true. So generally you would push things, but you have to see it in the following way. So if you didn't include the bias, then the models would tend to explode the magnitude of the parameters. The bias tends to counteract that by pushing things back to the origin. And the question is, are you doing it in the right balance?
You mean the prior?
Yeah, the prior will push you back to the origin in the L1 or the L2, the standard priors that you do. It tries to counteract this. So let me tell you what we're actually doing now, which is probably the best way, is to say that we don't take the hyperparameter as a parameter. No, we solve it on the basis of an extra condition, namely that the bias is 0. So the hyperparameter is then no longer something that you get. You compute it on the criterion that it actually precisely balances the overfitting action. Which is
that involves this replica.
That involves, because the replica method tells you, it gives you an equation then for the optimal hyperparameter.
Okay, thank you.
So we have one more question by Anatol. Anatol, do you want to ask it yourself, or if I don't hear from you, I'll just read it? I'll just read it. In many practical deep neural network applications, people train multiple models and use their divergence as a measure of overfitting. What are your thoughts on this?
That can be dangerous if you think about what comes out of these simple exercises where you plot true versus inferred parameters. Then you see that there are two effects. There's first of all noise, a broadening of the cloud, and there is a structural bias. So if all these different models were structurally similar, then they would all give you the same bias. So the only thing you would capture would be an estimation of the noise contribution. And it would give you a false sense of security because they would all give you exactly the same bias. So I don't think that would be a good idea, if at least these multi-layer networks, as I believe, will behave in a similar way in this sense.
Mm. So yeah, actually, again, a follow-up question on that I wanted to ask is that if you actually wanted to solve this regression problem that you have in practice with multi-layer neural network, then kind of those have the mysterious property that as you are adding variables, they don't have this kind of U-shape bias variance trade-off. They just like you overfit them and the test error seems to be decreasing. So did people try and see that on the kind of data that were motivating your study? Because that's just a generic regression task. So you could just hit it with some like deep neural network. Do I understand it correctly?
Yeah, I've never done this, so I don't know. I mean, the reason I took this model is not because I believe this is the best possible model in the world, but I've just accepted that the medics, whether you like it or not, they like it and they keep using it. So if that is the case, then I might as well see how I can repair the errors that that method makes. Multi-layer, yeah, I know multi-layer networks, but I haven't used them myself much. But this is, as I said at the end, this is next on the list, because in a multi-layer network, you will just have more dot products to worry about. Well, if you have one hidden layer, if you have deep, it's different. But the next step is one hidden layer and see what happens then.
Okay. And maybe if somebody has a last question, if not, I have one. Last one. And another thing I was wondering is the way your equations depend on the inputs. So you call them, oh, I forgot, Z, yeah. They depended on the covariance matrix. So in a sense, the result of this equation is as if the inputs were Gaussians with that covariance matrix. But is that really, I am kind of failing to say if I actually apply this for some very generic inputs that didn't come at all from a Gaussian, they will have a lot of correlations. Do these formulas still apply? I would think not, but you seem to be saying that all depends only on the covariance.
No. I mean, because this is what I said, I have to assume that this quantity is Gaussian. This is where it all happens. And for instance, you're absolutely right. I could choose a distribution for P of Z where only the first three components of Z are non-zero and the rest is all zero. I can forget about Gaussian statistics in that case. Yeah. Or when the Z's are exponentially distributed. So I need a sufficiently large number of components to be not entirely independent, but at least insufficiently dependent in order to use the central limit theorem here. And of course, it's not always valid. It has conditions.
So if you applied, for instance, for the type of Z's that come from the real data, is it valid? Like, can you plot what the regression, what the Cox model does on the real data next to the replica result, and do they agree? Maybe there was in some of the simulations, but they went too fast. I didn't catch which were just generated data and which were real data.
Yeah, so this was mostly synthetic data. On the real data, you can, in retrospect, plot these things. Yeah, you can plot the dot products. And generally, in most of the data that I look at, the medics try to measure things that are pretty orthogonal because they know that otherwise they waste a lot of money in measuring things that are measuring the same thing. So in most of the clinical data, many of these sets are pretty orthogonal, and then this is fine. But it is not guaranteed to be the case. And also in the theory here, we see that there are conditions on the matrix A. It cannot be, let's say, completely everywhere you have non-zero entries. They have to be reasonably controlled. And that leads you to mathematical conditions on the spectrum of A, which I didn't mention with just limited time. But I cannot use any A. It must be
I understand. And it has not been done yet to compare to data that come from the real application. That's
the next step. We're now sort of building it into our pipelines and applying it.
Great. We also have a question from Peter Solich. Oh yes, there is one. Peter, are you?
Hi Tom, can you hear me?
How are you?
I'm all right. Very good. I wanted to ask, you mentioned in response to Bert's question that you could choose hyperparameters to minimize the bias. How does that relate to optimizing marginal likelihood? Are these procedures ever equivalent?
I mean, it's this type of question I've also been asking myself, but in a slightly different setting. And I think it must be the same to what you're asking. For instance, I had this overfitting quantity E at the very beginning. I could use as a criterion the demand that E be zero. Yeah, and that's probably going to go in the direction of what you suggest. See, the reason I didn't do that is because out of the theory, I can compute exactly this bias. I can compute the expected value of the parameters, and I see this as linear related to the true one. So my target is to remove that bias. But so my guess is that what you suggest is equivalent to demanding as an alternative criterion that the overfitting measure E is equal to 0. Okay. But not necessarily that the bias is gone.
Okay.
Okay,
Right,
thanks, Don. Thanks, Don, for the discussion and for the talk. We will be moving on to the next talk by Manfred Opper.